Hey everyone, we're going to finish our lesson on electric circuits today, learning how to connect meters in a circuit. We'll talk about conservation of charge and power in circuits as well. Before we do that, I wanted to just kind of check our answer from the previous video, which we were doing on parallel circuits. And we got this value here of 8 amps for our total current. And I just want to verify that real quick using Ohm's law, which is V over R. And we could do this in the beginning. We knew the voltage here, and this problem was 24 volts. Once we found the equivalent resistance of 3 ohms, we can figure out that the total current from the source is 8 amps. And from there, we broke it down and figured out how much current was in each branch of the circuit. But just to kind of verify here, check your work, we can use Ohm's law to verify that as well. So moving on here to using meters in a circuit. Now I've put these in so far in each of our examples. And the two types of meters have to be connected differently. But just to kind of recall, an ammeter is used to measure current, remember amps, and a voltmeter is used to measure potential difference or voltage. How original of a name. That's potential difference or voltage. Now, as far as the type of circuit goes, being a series or parallel, the meters are always connected the same way, regardless of the type of circuit that you have. An ammeter is always going to be connected in series with the circuit element being measured. So we can see the ammeter here. It's in the path of current flow. It's in series. So if you remove that ammeter there, you're left with an open spot and the path for current is broken and the circuit would not work. Same idea over here in the parallel circuit. That ammeter is connected in series. If we remove that, at least that branch of the parallel circuit would not be working. A voltmeter is always connected in parallel. So the voltmeter here in the series circuit is connected on either end of that resistor. But if you remove the voltmeter, this circuit will work fine. Same thing over here in the parallel circuit. Since it's connected in parallel, there's multiple paths for current to flow. And by adding or removing the meter, it should not affect the circuit at all. So this is how our two types of meters will always be connected. Ammeters in series and voltmeters connected in parallel, regardless of the type of circuit. On to conservation of charge. This is a charge, not change, in electric circuits. This is conservation of charge. Same thing here, charge. I'll have to adjust that. Charge in an electric circuit must be conserved. Now, at any junction in the circuit, let's say we have a junction here, we'll call this junction P. The sum of the currents entering the junction must equal the sum of the currents leaving it. So if we have current coming into junction P, and we have two branches here coming out of junction P, the total current coming in here, let's say it's 12 amps, we have to conserve charge. So if 12 amps come into junction P, we need 12 amps coming out of junction P. So if we have 7 amps, let's say on this branch, what value would we have on the other branch here? Well, this would have to be 5 amps, because that total 5 and 7 gives us 12, leaving the junction P that came into junction P. And to verify that from our previous circuit, if we look at this junction here, we have a total of 8 amps coming into the junction. So we should have, between this branch and this branch, 8 amps. So 8 coming in, we have 4 coming down this branch, which means this branch has to have 4 amps. Now we have 4 amps coming into this junction here. So we should have 4 amps between this branch and this branch. We'll check that 4 amps coming in. We have 3 amps here, which means this one has to be 1 amp. So 1 and 3 gives us 4 amps leaving the junction, where 4 amps came in. That's our conservation of charge. Now, electric power, you're probably more familiar with this than you think. Electric power is the product of potential difference and current. There's a few different derivations of this equation that we'll see, but ultimately, power is the product of voltage times current. And the other derivations of that we'll see from Ohm's law are I squared times R and V squared over R. Depending on the type of problem or what you're given, you can use any of these. But power is measured in watts. And you guys should be pretty familiar with wattage. We did it previously in our unit on energy. And most of the devices that you use in your home are measured by the wattage that they use, which is the current times the voltage. And in the home, our voltage is generally around 120 volts. That can vary slightly, but it's about 120 volts. For a typical, let's say 100-watt light bulb, it will be the product of 120 volts times our current. And our current in this case comes out to 0.8 amps. So a 100-watt light bulb is going to use 0.8 amps of current. A lot of you in your assignments last week gave me different devices with the wattage. And I had mentioned to you, well, if you divide it by the voltage, then we can figure out how much current is actually being used by that object. The more wattage, the more amperage that is being used by a particular device. Now, an electrical circuit, electrical energy, which we'll call W, is equal to the product of the power that's being consumed and the time t of the charge flow. And this is how we actually get your electric bill each month. It's equal to the product of the power times the time that charge is flowing. I'll give you a couple derivations here. VIT, these are all on your reference table. I squared RT and V squared T over R, depending on what information we have available to us. Now, this is how your electric bill gets determined. It's based off of electrical energy. And if you look on your electric bill, you should see on there how many kilowatt hours you used during the time period, probably for that month. And the kilowatts, how much power you use, and the hour is the time of that charge flow. And this might be something like, I don't know, I probably should know what mine is, but it's about 20 cents per kilowatt hour, something like that. It's probably more than that, and it depends on your supply and your delivery, but I encourage you to check your electric bill and see how much electrical energy you're using per month. And they sell little devices that you can use and plug into your wall, and you can plug a device into it, and it'll tell you how much energy it uses, how much wattage it's using, or voltage, or current, or anything like that. They're pretty neat devices. This is also represented, because this is electrical energy, our unit that we'll use are joules. The kilowatt hour is just what you see really on your electric bill. Not really many other spots that you'll see that specific unit for. The remainder of what we have here for electric circuits is a summary, and I'm going to let you guys fill this in. I'm not going to spend time doing this on a video here, but basically I'll just kind of show you what you can do here to kind of summarize what we did in this lesson. A is equal to cross-sectional area of the wire. That's what we call the gauge. And its units are meters squared. You can do this for each one of these here and list these out. I think it's a great way to review what we covered here. This seems kind of like maybe not a whole lot of notes, but this is almost or will be about 70 minutes worth of video, and there's a lot to do with types of circuits. So I think taking the time and putting all this into this summary here will be beneficial for everyone. Important equations. This one comes right out of the reference table. Current, change in charge over time, passing a particular point. And if we rearrange that and solve for other variables, Q equals IT and T equals delta Q over I. We're just kind of rearranging those to find the different values here. For power, the other ones here, these are the other ones listed in your reference table for both power and electrical energy. To summarize the circuits here, we covered series and parallel circuits. You guys can draw on a simple series and parallel circuit here. The equations here come from your reference table. And I'm going to give you a little bit here on using these above equations properly, depending if it's a series or parallel circuit. Now for series circuits, we want to, generally given the current, we want to use the given current to solve for our equivalent resistance and voltage. And the part of Ohm's law that we use most common with this is I equals V over R. For parallel circuits, you're generally given the voltage. So use the potential difference or voltage. Use the potential difference given to solve for our equivalent resistance and current. And the version of Ohm's law that we're using is V equals R times I. Important part here to remember with the parallel circuits. Remember, you must have 1 over Req equals 1 over some value here. And this is going to be the value of our equivalent resistance as long as the numerator there is a 1. You can find the circuit symbols that we need for all of these on page 4 of your reference table. And again, I encourage you to take the time, fill in your symbols, fill in your equations, draw a example series and parallel circuit, and summarize with your equations here as well. And use these 2 pages as a kind of cheat sheet to help you with any of the problems that you see in this unit. You'll be dealing with a lot of questions dealing with series and parallel circuits, and I think this sheet will really help you complete all of them. Okay? If you guys have questions, write them down, make sure you ask them. Again, this is a huge portion of your Regents final, so make sure you ask questions if you are not sure on anything. Have a great day, everyone.